So the final reaction from our little table was alkylation. But as I told you, this is one of those few times in the A-level syllabus that you actually give credit to the people who came up with it, and it is called a Friedelcrafts Alkylation. The reagents, an alkyl chloride, or it could be an alkyl bromide, and AlCl3. So I'm just using an alkyl chloride here and aluminum chloride as my catalyst. I could have used the bromide and the appropriate bromide catalyst. Exactly the same idea for both. So we're going to break this up though into 3 discussions. First of all, we'll think about what if you have a primary chloroalkane. So I'm going to exemplify this with ethyl chloride or chloroethane. So standard thing that we saw back when we did the bromination. Here is our catalyst. That catalyst is going to come along and make a complex with the halide. And so we get this complex. And again, you saw this before when we did the bromination. It was Br+, and then the bromine here that was of course activated because electrons being pulled even more than usual by this complex here. So the CH2 was quite a bit slightly plus, just like the bromine was slightly plus. And so now we have our electrophile. Here's benzene. There is the electrophile coming in. Electrons go from the double bond to that slightly positive, and of course at that point that slightly positive carbon tells the chlorine to get lost. And so the 2 products that we have, there is our a tetrahedral carbon intermediate, the standard thing we've seen now, carbon on top bonding to its original hydrogen, plus the electrophile positive on the adjacent carbon to it. And we've also made some of this AlCl4 minus, which I'm drawing as the AlCl3 with that chlorine right there. Now at this point we've added the Z+, which was the activated alkyl group here. We now need to abstract the proton. Very much analogous to what we saw with the bromination. The electrons that were on this original chlorine anyway leave the aluminium and come down to the hydrogen, just like that. So the hydrogen breaks the bond to the carbon. The 2 electrons from that go to replenish the double bond. I've used that phrase now I think 5 times. And we get, in this case, ethyl benzene, HCl from the hydrogen that was abstracted by the Cl, and then of course we've got our aluminium chloride catalyst left back over. So a mechanism very, very, very similar to the bromination mechanism. You use your catalyst, which pulls away that chlorine, or of course in the bromination it was the bromine, thus activating what's left. For the bromination it was the end Br that got made slightly positive. Here it's the carbon that was attached to the chloride becomes even more slightly positive than it is anyway in that nice polar bond, and so we can then get the attack of that electrophile on the benzene ring. Now you will have been told a different mechanism for this, but I'm going to come back to that in a minute. But this is the more established mechanism where you have that activated complex rather than something else. Now the something else can be seen where if instead of taking a primary alkyl halide, we take a tertiary chloroalkane. So let's use my favorite one here. I call this tert-butyl chloride. You of course call it 2-chloro-2-methylpropane, but tert-butyl chloride is a much happier name for it. But anyway, the important thing is that the carbon attached to the chlorine is a tertiary one. So the same old stuff, there's the AlCl3, bonds starting to make between the chlorine and the aluminium, so you get this complex. But at this point, the carbon tells the whole lot to get lost. It says, look, take those electrons away with you and leave me as a tertiary carbocation. Tertiary carbocations, nice and stable. Primary carbocations, extremely unstable. So if on that previous page I'd said we'll make a primary carbocation, you should have said, but primary cations are really unstable. So that's why when you have a primary chloroalkane, we have that complex in which we don't actually break the bond between the carbon and the chlorine until we've replaced it with the bond between the carbon and the benzene. Here we break the bond between the carbon and the chlorine to make this nice positive carbocation intermediate before the benzene even gets involved in it. Anyway, the rest of this is of course exactly the same. There's benzene, there's our Z plus carbocation coming in. Electrons go from the benzene ring to the electrophile, and so we make our standard intermediate that of course you're very used to seeing now. The carbon bonded to its hydrogen, bonded to the electrophile, in this case that tert-butyl group that was the carbocation, positive here, and then of course we've still got this AlCl4 unit coming in. Same thing we saw before, abstracts the proton, giving us HCl, and our catalyst back again, and of course here we have the tert-butyl benzene, which would be what, 1,1-dimethyl ethyl benzene. It's so much easier to say tert-butyl benzene, isn't it? Anyway, so primary alkanes, you form that complex. Tertiary alkanes go through the carbocation. Now there is a little bit of an issue when you use anything but a tertiary alkyl halide, and it's most effectively illustrated using a primary alkyl halide. So here I'm going to go not ethyl chloride, I'm going to use propyl chloride or chloropropane here, okay? Because we're going to see what some people would term a carbocation rearrangement, and indeed carbocation rearrangements are extremely important. But let's just go through this. So we see the same bond making. Here's our complex. Okay, now of course at this point I've said to you, well, this was a primary alkyl halide, this is a primary carbon, so we're not going to break the bond to the chlorine and make a primary carbocation. We're going to take the complex that of course has this as a nicely slightly positive atom that's going to bond as usual to the benzene. I haven't messed around with the intermediates here, just straight from here to the product. Okay, so it's the CH2, CH2, CH3, right there, CH2, CH2, CH3. So that's what you would expect by what we discussed on the primary alkyl halide movie. But when you get to this stage, this hydrogen that I've moved in red can actually take its electrons from this carbon and bond to this carbon. So let's draw a little curly arrow here, because of course this carbon is the slightly positive one, and so the electrons can go from there to that, and we make this species. So electrons to that carbon from the hydrogen, so now the carbon bond breaks the bond to the chlorine. But now it's not the carbocation on that primary, we've instead moved the hydrogen from this carbon in a so-called 1,2 hydride shift, right? Moving the hydrogen from this carbon to this carbon, and we've made a secondary carbocation. Now, of course, secondary carbocations aren't as good as tertiary carbocations, but they're not bad. They're certainly better than primary carbocations. So when you have a primary alkyl halide, you can have it so that the alkyl halide adds on in a primary fashion, as we see here, or alternatively, some of it can undergo a 1,2 hydride shift when it's made this complex with the aluminium, okay? And now it's the middle carbon that is the one that is positive, this middle carbon that is the electrophile. So now when you put benzene there, you make this. So it's either the propyl benzene, or else what I would call isopropyl benzene, or you would call 1-methyl ethyl benzene, okay? So you can have a mixture of products whenever you use primary and even secondary alkyl halides to do Friedelcrafts alkylations. Tertiary alkyl halides, great, because you make that tertiary carbocation. There's some potential messing around with tertiary carbocations, but nothing we need to worry about here. So a tertiary alkyl halide will give you the tertiary carbocation, which will make the benzene complex. However, primary alkyl halides, secondary alkyl halides, used as the reaction. When you get to this complex here, you can either have the complex reacting as we've said before, or you can have some rearrangement, in this case the 1,2 hydride shift. So Friedelcrafts Alkylations, even though they've got a nice cute name, aren't necessarily the most useful reaction for making primary and secondary alkyl benzenes.